Hello everyone, welcome to aplusbi. This channel is all about complex numbers, and in this video we're going to be solving a really nice complex equation. Now, where does the idea for this problem come from? I'll tell you in a little bit, so hopefully you'll have an idea. By the way, if you're new to complex numbers, go ahead and check out my lecture videos. If you like algebra, number theory, trigonometry videos, go ahead and check out my other channel, which was the very first channel that I started, Cyber Math, cyber with an S. I keep saying it because normally cyber is spelled with C. By the way, I'm not from Siberia. Anyways, a lot of people think that way. So we have this equation. How do we solve for Z? To make it more clear, I made it red Z. Hopefully that's more clear. Now, we have Z minus I to the power Z equals 1. And by the way, there are different variations of this problem. If we had not 1 on the right-hand side, could you solve an equation like this, right? I'm talking about like analytical solution, not an approximation, not a numerical method, because I don't like numerical methods. I mean, some people like them, but I don't. Too bad. So how do we solve such an equation? You could probably think of it this way. Okay, the base needs to be 1 or negative 1, and the exponent needs to be 0, right? Or if the base is 1, exponent can be anything. If the base is negative 1, exponent must be even. If the exponent is 0, then the base can be pretty much anything, including 0, because 0 to the power 0 equals 1. You don't believe that? Go ahead and check out my video. Hopefully I won't forget to share it here as a card. So how do we solve an equation like this? Obviously, the method that I just talked about applies to real numbers, mostly integers, good solutions, competition type problems. This one is different because, come on, this problem is about complex numbers. All right, so we're going to have to be more careful. How do we solve these kinds of equations? We could probably ln both sides, right? We could just say, okay, let's just ln this and ln that, but ln 1 is 0, so we get this to the front. We get z times ln z minus 1 equals 0. From here, we can just proceed with the solutions, right? Or you can make it a little bit more fancy looking and use what's called the complex exponentiation, or the definition for, yeah, I guess that's what it is. So here's how it works. Whenever you have something like w to the power z, that can be written as e to the power z ln w. E is Euler's number, and Euler is awesome because he's the best, okay? So argue if you want in the comment section down below. So we have this conversion to Euler's formula or Euler's form because we could also write 1 that way. So that's a nice way to do it. This way we're not going to miss any solutions, hopefully. Let's do it. So in this case, w happens to be this. So z minus I to the power z can be written as e to the power z times ln z minus I. And that's equal to 1. But instead of 1, I'm just going to write e to the power 2 pi ni, because that's what 1 is. Make sense? Okay, in the complex world, of course. And also, if n is equal to 0, then you actually get the real one. Okay, but this is the complex one. So what do we get from here? We get an equation, an exponential equation. This means z ln z minus I is equal to 2 pi ni. How is that possible that z is multiplied by the log of a complex number like z minus I, and then it is equal to an imaginary number like 2 pi ni? Because think about it, the real part is 0 on the right hand side. So could we possibly assume that, okay, z can be written as a plus bi? Absolutely. If you do that, you're going to get something like this: a plus bi multiplied by ln a plus bi minus I, and that's equal to 2 pi ni. So in this case, there's a couple different scenarios. Like, this could be a real number, in which case this also needs to be an imaginary number. So in other words, a would be 0, which means z is a plus bi. So if a is 0, z must be imaginary, right? Well, may or may not work. We're not exactly sure because we kind of need to dig a little deeper. So what can I do? I can go ahead and try to write the logarithm of a complex number. How do you do ln of a complex number, especially when it's in this form? Let's put it in standard form by putting together the, what's it called, the imaginary parts. Now we have to think about the natural log of a complex number. I don't even know if we can solve the equation this way, but I'm going to give it a try and then give you the cheap, easy solution. Okay? Now, if this is my complex number and I'm trying to natural log it, we got to remember, what is ln of a complex number? Z. And by definition, it's ln absolute value of z, or the modulus, plus I times the argument of z. And of course, if you pick the principal argument, you get the principal value, which we usually write with uppercase ln. I don't think we need for this because that's a real value. And in this case, you would use an uppercase A for the argument, which means the principal argument, which means we don't need to worry about adding multiples of 2 pi, just like we did here, right? So anyways, no matter how you do it, let's just kind of stick with a more general form. Maybe if needed, we can simplify the process. But in this case, we know the absolute value of z is square root of a squared plus b minus 1 squared. The problem is we don't know the argument. But argument can be found from arctangent. And remember, tangent theta is b minus 1 over a. So in this case, that will be our number. Now, this number is multiplied by what? A plus bi. So we're going to go ahead and multiply these two things, and that's supposed to equal 2 pi and I. You get the idea? And of course, in this case, I'm going to go ahead and distribute everything. This looks like it's going to work, but who knows? This is pretty complicated. So let's go ahead and distribute this. We're going to add real part. We're also going to get real parts from here. I times I is I squared. That's going to bring a minus sign. And b times the arctangent, or like bark tangent, right? It's kind of funny. I hope you find it funny too. And then the imaginary parts, that's going to be quite complicated. But here we're going to have b times the ln of this. And then there's another piece. Where is the other imaginary? Yes, it's going to be a times the arctangent, b minus 1 over a. And of course, that needs to be multiplied by I so that it is the imaginary part. Make sense? Now, this is equal to what? Great. It's equal to 2 pi and I. What does that mean? This is equal to 2 pi and I, which means the real part is 0. Cool. This whole thing is 0. Can you solve that equation? I don't know. But we also know that this part is 2 pi n. So that gives us a system of equations which is probably very, very, very difficult to solve. So let's go ahead and look at some special cases because this is not really getting anywhere. I was hoping that it would. Maybe it does, and I'm missing it. Please let us know if you have a solution. But definitely work on this equation because it's a really nice system. I'm kind of lazy, so I'm going to give up on that and leave it as an exercise for you. And don't hate me for that. Okay, so this is our equation, and how do we solve it in the simplest way possible? Like I said earlier, okay, this can be 1. So if z minus I is 1, that means z is equal to 1 plus I. And there you go. We got a solution. Why? Because 1 plus I to the power... Wait a minute. I messed up. Okay, z is 1 plus I. So 1 plus I minus I to the power 1 plus I is 1 to the power 1 plus I, which is equal to 1. Because when you have 1 at the base, the answer is always 1, right? I hope so. Okay, so it looks like z equals 1 plus I is a solution. I don't think 1 minus I will work. You can find another solution. You can try it. For example, is negative 1 plus I going to work? Give it a try and let us know. But we could also consider 0, right? I mean, if z is 0, look at this. If z is 0, then we get negative I to the power 0, which should be 1 again. So it looks like we got two solutions, at least 0 and 1 plus I. And are there any other solutions? That's for you to find out and let us know. And this brings us to the end of this video. Thanks for watching. I hope you enjoyed it. Please let me know. Don't forget to comment, like, and subscribe. I'll see you next time with another video. Until then, be safe, take care, and bye-bye.